Electron microscopy uses an optical microscope design, but a wavelength 100,000 times smaller than visible light. Transmission electron microscopy is the only technique that can directly image viruses and proteins in 3 dimensions. It is the predominant method for imaging the intricate interfaces in state-of-the-art semiconductor devices. It is the only imaging technique that can get to the subatomic resolution in 3 dimensions. This type of microscope is intertwined with our daily life. We can talk about an electron microscope in 3 parts: source, optics, and detectors. The source forces electrons to quantum mechanically tunnel through a potential barrier. These electrons are then accelerated through 300,000 volts to about 3/4 the speed of light. The now relativistic electrons travel through a series of 2 Tesla magnetic fields that act as convex lenses. The electrons interact with the sample and produce an image that is magnified by nearly 1,000,000 times before it is captured on an electron detector placed about 3 meters below the electron source. The sample is inserted into the electron beam's path on a small rod keyed to move through an airlock into the high vacuum region in the center of the microscope. High vacuum embedder is required for the electrons to travel from the source to the detector without being significantly scattered. The vacuum system, which uses roughly 10 different vacuum pumps, and the water cooling system required to keep the magnetic lenses from overheating, are significant complications in the electron microscope when compared to an optical microscope. All the machinery involved must be carefully linked together to inhibit disturbances in images at atomic resolution. Biological structures are bound by chemical bonds that are very sensitive to the beta radiation produced in an electron microscope. We can make several copies of these beam-sensitive biological structures to spread out the radiation damage. By imaging nearly 1,000,000 replica, we can average them together and produce a single structure with atomic resolution. But there's a problem. If our structures have fewer than about 10,000 atoms, it becomes hard to differentiate the background of the support. We need another method to direct imaging. What we need to do instead is build a crystal, a type of scaffolding that can house these 10,000 atom or less units, and scatter electrons from this crystal to determine the structure of the repeated units in the lattice. This technique has many variations, but the one we'll be talking about is microelectron diffraction. There are many ways X-ray crystallography methods can be used to solve the structure of repeating units in our crystal. X-ray diffractometers and synchrotrons are used for large and medium-sized crystals. But if your crystals are too small for these methods, say about a micrometer in size, about 1/10 the width of a human hair, we can illuminate the crystal with an electron beam. After a few minor corrections in parameters, electron wavelengths are much smaller than X-ray wavelengths, for example, we can then process this diffraction data just like we would data from XRD or synchrotrons. This diffraction technique is very beneficial for small molecules. Small molecules, those with 10 to 100 atoms in them, are extremely important for chemistry. These molecules are too small to image directly, and the crystals can be too small for conventional X-ray crystallography techniques. They are well suited to be studied and solved using electron crystallography techniques such as microED. The electron microscope is a Swiss Army knife of microscopy tools. In addition to high-resolution imaging and crystallographic structure determination, it can perform a variety of other imaging and spectroscopic modalities. 2 of the most common are 4-dimensional scanning transmission electron microscopy, also called 4D STEM, and energy dispersive X-ray spectroscopy, EDS. 4D STEM means taking a diffraction pattern, a 2D object, at every point in an image, another 2D object. With this information, you can determine different structure components from the locations of certain diffracted electrons, or select particular scattering ranges to highlight important contrast. Tychography is one of the most quickly developing 4D STEM applications. Using almost all scattered electrons, you can reconstruct your image beyond the diffraction-limited resolution down to sub-half angstrom resolution. At this point, you're starting to see the interior of atoms. What makes this microscope special for BioPACIFIC is the speed at which it can acquire electron crystallographic data. Using microED, we can take data as quickly as on an X-ray diffraction tool and faster than time-limited synchrotrons. Using the software automation tools in electron microscopy, we can take data from hundreds of crystals. We can use this speed to rapidly screen samples and acquire high-precision structure solutions. What better way to accelerate and sustain domestic material discovery and deployment, the mission statement of the Materials Genome Initiative, then to rapidly analyze microscopic crystalline samples using electron microscopy. NSF's BioPACIFIC Materials Innovation Platform can leverage this tool's capabilities to be an essential part of the design, build, test, learn cycle at the heart of this program's mission. This will help facilitate research into dedicated and scalable production of bio-derived building blocks and polymers from yeast, fungi, and bacteria.